I suggest we can start with the webinar. So, hello everyone who is present. Welcome to the TMSI Expert Talks. This is our sixth webinar. I am Leonie Terstegen, and it's an honor for me to be your host for today. First of all, I would like to give a warm welcome to the speaker of today, Dr. Petra Fischer. And Dr. Fischer is a postdoctoral neuroscientist from the University of Oxford. And her research involves neuronal synchronization during movement in the subthalamic nucleus. And the topic of today's talk will be the cortico-basal ganglia gamma and beta synchronization during action control. And before we start with the presentation, I would like to mention some house rules. First, as an attendee, your microphones will be automatically muted. So if you have a question during the presentation, you can use the Q&A button, which you can find under the middle center of your bottom screen. Here you can type in your questions, and after the webinar, I will go through the questions one by one. Then if there are any additional questions during the presentation or after the presentation, you can use the raise your hand button and I can unmute your microphone. And so you can ask your question yourself. Then first, we are with now 24 attendees, and I hope you will all enjoy this webinar. Then I would like to invite Dr. Fischer to take over the words, and the floor is yours.
Thanks a lot, Leonie. As she already said, I will talk today about cortico-basal ganglia recordings. And specifically about our findings in relation to action control. I will start with a background on oscillations and motor control, and then I will talk in more detail about two studies. So why is it interesting to really study oscillations and motor control? In our lab here in Oxford, we're really motivated by the perspective of improving treatments for movement disorders. For example, Parkinson's disease or essential tremor. So we have, for example, a treatment stimulation where we implant an electrode to the basal ganglia or the thalamus, and it works really well for a lot of patients. But there is some drive to really improve on the current way of stimulating by using oscillations as a feedback signal. There are also ideas, for example, of trying to improve symptom control by providing neurofeedback training by feeding back some brain signals. Or some studies also done, for example, in our group, they have tried to use non-invasive stimulation, for example, using peripheral tactile stimulation, again, for example, to try to reduce tremor. And you could then again try to interact with what brain oscillations you measure. And also for me personally, so this is one of the main motivations also why I started my work 6 years ago, why I chose to do that PhD. This was really my main drive. But now I also really became more and more interested in really understanding how different parts of the brain communicate and interact with each other to enable movements. And that's just one quote from a recent publication where they said, a confusing but consistent finding is that most transient STN responses, that's a part of the basal ganglia, they can result in both increases and decreases in firing rates for both stop and movement responses. So even when you start a movement or when you stop a movement, you can see both changes in firing rates. So looking at firing rates alone really does not seem to be sufficient to make sense of these recordings. And one hope is that looking at oscillations in different parts at the same time will really help us understand what interactions happen. So what do we already know about the relative timing of neural activity? That was in a way where we started, so before these two studies that I will talk about. One very stereotypical observation that has been reported over and over again is that when people perform a movement here at time point 0, then you can see in the time frequency decomposed signals, here you can see the different frequencies up to 100 Hertz. You can see that power in around 20 Hertz around the beta range, which we define between 13 and 30 Hertz. That goes down, while at the same time, gamma power here between 60 and 80 Hertz approximately, that goes up. And so that is a recording from motor cortex in an MEG study and the subthalamic nucleus, which is again part of the basal ganglia at the same time. And you can see the same pattern happens in both structures. And because of this, because gamma goes up during movement, people have thought always, oh, this is maybe a signal that reflects a prokinetic command, or that it helps you to move, it facilitates movement, while beta activity has to go down because beta activity otherwise would potentially be anti-kinetic, would prevent you to move, or it would potentially stop or interfere with a movement. So that was the broad idea. And I will discuss in more detail now how these two different types of oscillations actually behave in slightly more complex or slightly different tasks than just a simple movement. And why am I talking about the subthalamic nucleus, the SDN? I already mentioned it a couple of times. So here you can see a schematic of the basal ganglia and inputs from cortex and from the thalamus. And you can see that there is substantial convergence. Those are just the numbers of a rat brain here. So millions of cells in cortex project to a relatively small number of cells in the SDN. And also within the basal ganglia, the other input structure here has a considerably larger number of cells, but they also send inputs down to the SDN via this other nucleus here. And we know, so why is it really interesting? The SDN is one target of the deep brain stimulation electrodes that seems to be working really well in improving Parkinsonian motor symptoms. So when you switch on stimulation here, then usually motor symptoms improve. But another really interesting aspect of it is that it also seems to have a role in rapid stopping of an action. So if you do, if you ask people to perform a quick stopping task, then we can see certain prefrontal areas becoming very active that in turn seem to activate the SDN through that so-called hyperdirect pathway from cortex that then somehow seems to be playing a role in canceling the movement. But how exactly that happens, those details still need to be worked out. And what I also added to this diagram are these two dashed circles that indicate that there is recurrent connectivity. So the SDN excites the GPE, one of the basal ganglion nuclei, which in turn inhibits it. And as soon as we have these recurrent connections, that is then very likely to result in oscillations. For example, if this would be activated, but this would then inhibit it, you can imagine easily how you have this rapid change between firing and inhibition and firing and inhibition within this part. And so here now I talked a bit about what's happening during movement initiation, but we can also think of other motor control functions that are also really essential. So what we generally are able to do is to rapidly interrupt an action based on what's happening around us. For example, if you would want to hunt prey, it would be very important to be able to react very quickly to what's happening. And I call this here, this is some form of transformative control, because when the neural dynamics are initiated that trigger a movement, but then suddenly some sensory information requires this to be changed, then you really need to transform what's happening into a very different direction. So that's the first point. And the second point is when we want to ease into a sustained contraction, for example, when here you try to pull that back before you shoot the arrow here, you somehow want to stabilize that posture, and somehow the neural dynamics also then potentially need to be stabilized to be able to hold that. And on those two different motor control functions, we performed studies and we recorded motor cortical EEG activity and also local field potential recordings from the SDN and also from the GPI in one of the studies. So in the first study, I will talk about sudden stopping of an ongoing movement. And the task was relatively simple. Patients would hear a sound, a beep tone, and they would perform tapping movements in rhythm to the sound. And at the end of a random number of sounds, they would suddenly hear a higher pitched sound, which was the stop signal. So I'll just quickly demonstrate it. Doop, 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 doop. And then in a way, you have to hold the finger up instead of moving it down. You shouldn't make that very last tap. And we also manipulated the timing, the relative timing of this, so that patients will be able to stop in about 50% of the time. And that is one difference now to the very traditional or conventional stop signal tasks, in that you don't interrupt that command of performing a button press, but you really interrupt a movement that is already ongoing. So this tapping task is a fairly continuous movement task here. And first we looked at what's happening with each tapping movement. And as I already showed you, we see this stereotypical decrease in the beta range here, and at the same time an increase in the gamma range up here. So that's happening during the movements. And now during stopping, which is represented as the red line is the time of the stop signal. So this is when patients suddenly know, okay, now I really have to cancel my movement command. We saw this really sharp and fast gamma power increase. And one could then think, okay, well, this movement potentially involves when you move it down and up, potentially you may actually make two movements. And it wasn't actually really a stop, but for this we also performed the control analysis where we looked at EMG activity that we also recorded from that finger that performed the movement. And on the right side, you can see the blue line. That is when participants stopped fully without making any additional movement. This is where they moved a little bit, but they actually managed to stop halfway. And this is where they failed to stop. And you can see that the gamma power increase, it was highest when they didn't move at all. So this increase did not occur due to some additional muscle co-activation when they stopped only halfway. It was really strongest when stopping was most successful. And then we had an additional control condition because that sound, the higher pitched sound, it was especially salient. It kind of stuck out from the other sounds. And for that control condition, we had exactly the same sounds, but we told participants to not even try to stop, but just finish off with 2 more taps. So there's no time, there's no pressure to change or react quickly to that sound. And in this instance, which is represented by that black line, that is where they didn't attempt to stop, but after that stop signal, we don't see a gamma increase again. So it really seems to be linked to that cancellation of the movement and not to the processing of that high-pitched sound. And what I didn't mention so far is that usually during movement, you can see that this gamma power increase, you can see that in also the thalamus and in an output nucleus of the basal ganglia. So you can see that throughout the whole network. And that is also phase coupled, so that is coherent throughout the network. And in this study, we then also looked, okay, we saw this increase in the SDN, we didn't see the gamma increase in cortex. So what happens to gamma coupling? And we saw here, that's in green, that gamma coupling rapidly dropped after that stop signal. So in a way that the phase alignment that would usually happen during gamma power increase during movements, that was destroyed or wasn't there anymore during stopping. So something very different happened at the point in the STN and in the motor cortex. And in the beginning, I also told you that usually it was beta oscillations and the lower frequencies that were thought to be anti-kinetic, that are related to not moving. And when we looked at what's happening in this beta range, then here we actually don't see a significant increase, not at all. So that would be the STN and that would be the motor cortex. And so it really seems to be that this gamma increase is the more relevant thing that is happening in this specific task. Because in other tasks where, as I mentioned, where you do not move at all, but you actually retain your current posture, often studies did report a beta increase here at this point. Okay, and I'm now going to move to my second study with the question, what synchronization phenomena occur when easing into a stable contraction? And the task was to control the force with this pen on a graphic tablet, which would, the harder you press, the more this cursor, the black cursor square, would expand. And if you reduce the pressure, it would shrink again. And the visual cue was this blue square, and it would change randomly its size. So sometimes it would be very big, sometimes smaller. It could either shrink or expand from one moment to the next. And the task was, as soon as this would change size, they would also have to change the force and match that. But one of the recordings was for 2 minutes. So again, this was a continuous task, continuous motor engagement, where they slowly controlled this pen. And in total, we recorded 4 sessions. So we had 8 minutes of these recordings. And in some patients, we also had an off-medication recording. So that was performed. The other, all of the patients were performed on medications. So here we have 18 patients. And here we also have a couple of STN patients and GPI patients. So that's a slightly different nucleus in the basal ganglia. But we saw that in terms of the beta power time course, that looked very similar in the STN and the GPI. What I show here to the left, that is the behavior. So they had to either increase or decrease the force, and the force rate, so basically the speed of how quickly they did that, that was slightly faster when they had to decrease it. So that was a bit faster. And when we look then, what I show you here on the right is what happens to beta power. That is between 15 and 30 hertz beta power. We can see that before, so on the x-axis, I show you this is exactly the time of an adjustment. So I basically took all the force adjustments, all the increases and decreases, and tagged at the start of this and the end of this. So this was a stable period, and this was another stable period. And you can see that before they start the adjustment, beta power already drops here as well. And it already seems to slowly return before actually the adjustment was completed. So here especially goes up already before this is completed. So that's quite interesting, because usually when we just do a ballistic movement, it looks like beta power is just suppressed completely. But here, so they do this movement, and even before it's completed, it returns. And what we already saw here is that when they perform those decreases, which were faster, then beta power was more strongly suppressed. And now actually, so that's the average over those 18 patients. But on the next slide, I really want to show you single trials examples. And that is a decrease in force. So that's the force level. And here it decreases, and here it increases. And in both cases, the patient here performed a small, or kind of made a small plateau, which means it wasn't just a smooth decrease, but here basically it stopped a little bit and then it decreased further, and the same here, it increased and stopped a little bit and increased further. And what we look at now in blue, that's beta power at the background. And those bumps here, that represents the amplitude of, and whenever it has a high peak here, it basically reflects that there was a burst of beta activity. So during this period, it was high. And what we can see is that these periods where the force rate was very, very slow, they seem to coincide with these bursts of beta activity, as if it could really have a functional role in slowing down that force rate. And especially here, when it stabilizes again, you can see how it increases, or here as well, how it really increases. And one interesting finding that was related to that was that when they didn't perform the adjustment so well as here, in these cases, it was fairly accurate, but sometimes instead of finishing here nicely, they would move too much and then return. And when they move too much, and when we look at, oh, what's happening before here, we can also see that beta power was relatively low when it didn't manage to stop properly. And finally, one question, again, because we had these two types of recordings, the EEG and the subcortical activity, we again looked at what's happening to coupling, again, suggesting like, oh, how strongly do those two regions somehow communicate, how strongly are they linked? And here, ISPC, intersite phase clustering, that's a measurement of how well aligned the phases of beta are in motor cortex and the basal ganglia. And you can see that in green, all of those patients, they had a reduced coupling at the start of the movement. Again, also when beta power was low. So it kind of makes sense that here coupling is reduced. And here at the end, it was already significantly higher, again, the phase coupling. So already here, some sort of phase alignment in this motor network in the beta range seemed to emerge. And one short note, what we also found in this study when we compared patients that were on medication and off medication, where off medication also usually local SDN beta power is higher, we saw that actually the coupling was more readily modulated when patients were on medication, while when they were off medication, we didn't see the significant decrease in coupling, as if the system was locked in this high beta state in a way. And when we looked at how the speed of the adjustment covaried, it was in the on-dopamine condition, it covaried nicely with the strength of beta coupling, but off medication, it covaried then more with local basal ganglia beta power. So seemingly here, really the dynamics shift in terms of how well coupling throughout the motor network can be modulated. Okay, now we'll summarize these two studies. So first, I showed you that during a rapid stopping of an ongoing movement, we saw this local SDN gamma power increase and decoupling of cortical SDN gamma synchronization. And when we looked at easing into stable contractions, which is also in a way a form of stopping, but quite a different one, that seems to be facilitated by beta oscillations. So again, I will use those terms that I introduced already in terms of transformative control, where you really need rapid and major shifts in ongoing neurodynamics. That seems to happen when you start to move, so from rest to move, where you see this major shift, but also when you're already performing a movement and then suddenly stop. And as I said, we see these gamma oscillations during that period. And on the other hand, the stabilizing control, where you, for example, move and keep muscles contracted, but potentially another example would be to rest and to stay in the resting state. For example, when you cancel a movement before it actually was initiated, that's where we then see increased beta oscillations. And that's now just some discussion about what the more detailed mechanism could be, or is there, the question, is there really actually a functional role to these oscillations that I described? As I said in the beginning, I think it can be very useful to really look at what regions potentially drive what, which other region. But one question that with that finding during stopping is that if we look again at that diagram, and let's say cortical regions are alerted that now you have to stop that movement, and that would just suddenly increase firing and excite the STN, then again, that gamma increase could just originate from this setup here, and it could be entirely epiphenomenal without actually really being relevant to the function. But if we think of what it could be doing is that if we have during movement initiation, if we have these rhythmic spikes, rhythmically occurring spikes at around 70 Hertz, then if we have a shift in spike timing at any stage here where we have inhibition coming onto these rhythmically active regions, then this may be a really efficient way of canceling the activity. And for example, one observation that I haven't discussed in detail in the paper that was published there, but looking at it, the key frequency or strongest power increase at this last tapping movement seems to be at around 90 Hertz, while the strongest power increase during stopping was slightly less. And again, that change in peak frequency could also indicate that here, the windows of activity here that would then cause prolonged inhibition of the thalamus, that they could be longer than during the movement and when the movement was executed. So this is something that I'm really interested in and would like to look into further in future projects. And yeah, this leads me also already to the open questions. What I haven't been able to answer is what ensembles engage in movement and stop-related gamma oscillations. It would be nice to also have single cell recordings and then really look at the same ensembles engaged, or is it different ensembles that are involved in these synchronization phenomena. And also, what comes first? It's not easy to answer. It's a very difficult question, but can we maybe detect subtle changes in the timing of spikes, potentially already in cortex? Like how synchronized are they before we actually start a movement, for example? Do changes in synchronization precede potentially changes in firing rates? And also, again, for the stopping study, does cortical activity potentially is it already gamma rhythmic before it triggers activity in the STN? Is it already gamma rhythmic within cortex already? And in terms of the second study that I showed to you, where we investigated that stable contraction, what cortical inputs are required? So it seemed to be that, oh yeah, we saw beta oscillations increase, but is it that activity again going into the basal ganglia, is that already beta rhythmic potentially, or is it something within the basal ganglia potentially that produces the beta rhythm? And finally, the question of causality. At the moment, we can really more only speculate, but ideally we could then interfere with these rhythms and really see can functions still be preserved. And we could use different tools, for example, TMS, which could also be used in combination with EEG recordings, or we can stimulate using deep brain stimulation electrodes. We can have brief pulses, but in both cases, we will always really just involve a large population of cells that are probably functionally quite segregated usually, but we cannot be really spatially specific. And for that reason, maybe even neurofeedback training. So there are some studies in monkeys that have trained them to upregulate beta or gamma oscillations and then probe certain movement tasks after these different states were induced using neurofeedback. So that's something that would be very interesting to look into the future. Yeah, so with that, I'm already finished. And I would like to thank everybody that I've been working with in the last 6 years, especially Peter Brown and Huiling Tan. And that's already Leonie's slide. Yeah, I'm happy now to take your questions. Please, yeah, ask me whatever you want to know.
Okay, thank you, Petra, for your inspiring presentation. It's a really interesting research topic, so thank you. I will look at some questions. I don't see any questions yet. Oh, Leo, somebody has raised their hands, so I will unmute. Leo, 1 second. Here we go. Leo, Hogendoorn, you can take the word.
Yeah, Dr. Fischer, thank you very much for a very nice presentation. It's a very difficult matter, and obviously in order to understand it and develop better DBS treatment, so to speak, you need to get all these questions answered, right? I have two more technical questions. One is, you measure DBS and EEG at the same time, but obviously you can't do that at all times, right? Because people don't have wires hanging out from their DBS lead. So do you do that during change or implantation of the device?
Yes, that is a good question. So here in London and Oxford, often the procedures are performed in 2 stages. So that's when the electrode is implanted. Then the pacemaker often gets implanted a couple of days later, so that the whole procedure is not too long, because the first bit of inserting the leads already takes quite a while. And it's in that period where patients often really sit on the ward, and we can then ask them to do experiments if they want to participate. And at that point, we don't have an EEG cap, but we really have individual electrodes that we position then on our regions of interest, because you have the burr holes, like the wounds with the leads coming out. So that's how we do it. I know that in other places they do intraoperative recordings. And yes, in general, it would be nicer to do these recordings also if there would be a battery exchange, because one problem that is always can be present is when the lead is inserted, it can cause micro lesions and then a stun effect, which means that often, especially if somebody is interested in on and off medication effects, often patients are already much better just straight after the surgery without stimulation even being switched on, just because of those small micro lesions. But that also suggests that brain activity is changed to some extent, that, for example, if you then look at changes in dopamine on or off, it's potentially, you probably won't see as much as if you would do it later, like when DBS has been already in there for 2 or 3 years, and when it exchanged the battery, potentially that would be a better recording window. But in general, that is that small time window where we can do it here.
Yeah, but that allows you to do the things that you showed, sitting behind a monitor and using your arm, etc., because quite a few people just implant and place the lead and implant at the same time, right?
Yeah.
Okay, that explains it. Yes. And my second question is, you said that neurofeedback may be a promising tool for some of these patients. What exactly do you do then? How do you train the neurofeedback? I may have missed that in the beginning.
So I personally think that at the moment, the effects of deep brain stimulation, they are definitely stronger than, for example, trying to give them a beta neurofeedback signal from the STN. That's one study done in our lab where they've trained patients to down-regulate it and then ask them to press a button or do a pinching task, I think it was, and they were slightly faster after them having down-regulated beta activity. But I think to really have a proper improvement on motor symptoms, they would really have to train that a lot. And as a treatment for motor symptoms, deep brain stimulation itself is much more powerful. But what I meant in that last slide, that specifically also more to understand what is the functional role of oscillations instead of really trying to tackle the motor symptoms. I mean, in this case, it would be trying to upregulate beta or gamma oscillations before asking patients to do again a very specific movement task, and then trying to see while recording that signal and seeing, oh, do they actually really change their state in a substantial way, and does this then have an effect on their motor performance? But for symptom improvement, as I said, definitely DBS is more powerful than a neurofeedback. But it is something that is also even being pursued with using fMRI, I think, trying to up or down regulate certain regions in the basal ganglia in patients with Parkinson's. I think it's very interesting from a scientific perspective. Does this have an effect on behavior? But for patients itself, it would potentially work if they would really be able to train daily, but then you can't provide the STN-LFP signal on a daily basis. It's really only possible in a short window at the moment.
Yeah, so if we could bring out the STN signals at all times and not just in this time window between the lead insertion and the pacemaker placement, then you would have more time for neurofeedback, so to speak. Is that?
Yes, exactly. Yeah. And in Medtronic, they have now made a device available that has been implanted in a couple of patients already in different places, where you can actually stream even when everything is closed. So everything is healed and the patients are basically back at home and living their everyday life. So even then you can access the LFP data just via telemetry, and you can also potentially control the stimulator. So these tools are becoming available now, so that's quite exciting for that field.
Yeah.
But I have never worked with such a patient here before, but yeah, I hope to do that in the future as well.
Well, thank you very much.
Thanks.
Okay, thank you, Leo, for your question. Are there more questions? Otherwise, I have some questions. I don't see any yet, so I will first say, Dr. Fischer, your camera stopped working or stopped with working. So
thanks. I will try to get it back. Oh, where is it?
Yes,
back.
You're back. Yeah, for future applications, like, is it maybe possible that, how do you see that this can improve like the patient's life? Is it possible that the electrodes can recognize these patterns and then change the settings or something? Is it like the idea of, or?
Yes, yeah, so that is really quite exciting. I haven't talked in much detail here, but sometimes deep brain stimulation can cause side effects. For example, affect speech negatively, or it could also affect balance negatively. And sometimes patients already have different settings that they can adjust by like they just choose their speech setting, or they choose their walking setting. That can already be done, but it's all has to be done manually. So one idea would be to try to detect automatically certain motor states and then pick the ideal program accordingly. And then another line of research is to really stimulate only when necessary on a very short time scale. So work for my supervisor, it's now quite a lot of studies that suggest that when we trigger stimulation only when these beta bursts are high, then actually we also get the same or even a better clinical benefit while saving some of the battery life and while also keeping side effects reduced. One study showed that speech is less affected when it's in this more adaptive or intelligent stimulation mode. So that is something that is being still investigated. And one obstacle there is also really to these prolonged studies. I mean, it has been looked at for half an hour. And I know a few people who are working on that. And I think, again, maybe it has been slow because maybe the companies providing those electrodes didn't really have that hardware that would allow that to do it easily in a real world setting or in an everyday life setting. But now, as I said, it's becoming possible. And then for some people, it may really, really improve how the stimulation can improve the quality of life. And there's another line of research that is looking at oscillations, and that is looking into how, again, beta can be used as a biomarker to know where exactly it needs to be stimulated. In the newer electrodes, so the traditional one, they had 4 contacts, but some of the newer ones, they're split into directional segments, and they have then 6 contacts where you can pick the direction, and then 1 contact at the bottom and at the top. And it's actually really difficult for the clinicians to find out, which of the contacts would be the best one now. But again, if they have some information about how beta activity is distributed, that seems to be really helpful in then picking a contact and saving lots of time for the neurologist and for the patient, so they don't have to try out where should I actually stimulate, but they can follow what they can see in the brain signals.
Thank you for this answer. That would be like a great future perspective. Because you just mentioned about the clinicians, how the impact can be, how they place the electrodes or where they place the electrodes. Yeah, that has a major impact, of course, on the treatment. I guess every patient is different. Does this influence what you've been measuring? These signals, does that, like the placement, does influence what your measurements?
Yes, so at the moment I'm actually trying to reconstruct and verify the electrodes of 18 patients of one study, and I'm really looking at all the MR scans and CT scans and trying to find, okay, where exactly was the electrode. And in general, beta oscillations are quite a strong and relatively widespread signal, but what is sometimes a bit more difficult is to detect gamma oscillations, and that really also seems to be dependent on where exactly the electrode is. So if the electrode is in the dorsolateral part of the SCN, then usually also you should be able to see a gamma increase during movement. But in some patients we don't really see that, so that may be then in part due to where exactly the electrode is located. It's sometimes quite difficult to really make sure, because it's 5 minutes. It's such a tiny structure, the SCN. So and when you put in the first lead, the brain may shift a little bit before you put in the second lead. So those are all challenges. But as I said, one aspect could be this sun effect, that we did cause some microlesions and potentially have disrupted the normal activity, and that could potentially be a reason why in some patients also we don't see these gamma oscillations. Yeah, but this is there are again more studies that show. So one study with the title like the sweet spot for DBS, they have also mapped and looked where you can see beta activity, where this is strongest, and how that correlates then with that motor region of the SDN. Yeah, fortunately, because beta activity, it seems to be relatively, so not too extremely focally specific. So often we see it in, we tend to subtract the neighboring contacts, and we can sometimes see it in like 3 of those bipolar contacts, which means that it tends to be picked up quite well.
Okay, well, thank you for this answer. Are there more questions? I don't see any more questions. So then I would like to bring this webinar to an end. First of all, I want to thank Dr. Petra Fischer, of course, for her time and her wonderful presentation. So thank you. Then for all the attendees, all the related publications of Dr. Fischer will be sent to you by email. So keep an eye out for that. If you have any questions left or any remarks or comments, don't hesitate to contact TMSI. You can contact us through info@tmsi.com. And then we will make sure the questions will get to Dr. Fischer. Then I would like to use this opportunity as well to invite you all for our next webinar. We don't have a specific topic yet or a specific date, only that it will be in the end of November, but it will be announced on our website and on LinkedIn, and also through email. So I hope to see you all there. Then I would like to thank you all also for being present here today, and I hope you enjoyed this webinar as much as I did. Yeah, and then I want to wish you a good remainder of the day, and I hope you can all continue your research during these strange times, and stay safe, and hopefully see you next time. Okay, bye-bye.